us to our third and last presentation, actually. So good times pass by quickly. So this presentation is entitled Random Walk-Based Graph Representation Learning Revisited, and will be delivered by Arlei Silva from Rice University. Arlei, all yours.
Hello. So can you see my slides?
Yes.
Yeah, awesome. So really happy to be here to talk a little bit about this research. So my name is Arlei. I'm an assistant professor in computer science here at Rice. And this talk is entitled Random Walk-Based Graph Representation Learning Revisited, where basically we looked at this problem of linear representations for vertices in the graph and tried to answer some of the quick questions that were still open. So just to introduce you what representation learning on graphs is it's a way to solve graph combinatorial problems in a Euclidean space. So a lot of times, right, we are given a graph, so a set of nodes and edges, and you want to solve a problem such as link prediction, node classification, and so on. But solving these problems on graphs is really hard because graphs are combinatorial structures. So oftentimes we are interested in converting this data representation from a graph to a Euclidean space where you can apply linear algebra operations that are much more efficient and intuitive. For instance, maybe one way to predict whether there is a link between two nodes is look at the angle between the data points that represent them in this Euclidean space. And the goal of representation learning on graphs is actually learn this mapping, like how you go from the graph space to this Euclidean space where some operations such as inner products capture some notion of proximity. So that's the topic of this talk. And well, the most popular way to do representation learning on graphs is using random walks. And the idea is quite simple. It's inspired by models from natural language processing, especially this skipgram model, which does the following. So here is in the context of language. So you have a corpus of documents, and you can think of this corpus as a set of sentences. And what you want to do is to generate representations for words such that two words that occur often, they get embedded near each other. So this is a very popular idea, very powerful. It's the basis of a lot of popular models such as word2vec. And how you can translate this to a graph domain is by trying to generate something that looks like a sentence in a graph. For instance, the way that this is done is by trying to extract random walks from the graph and assuming that those random walks behave like sentences. So if you sample random walks in a graph with just a random sequence of nodes, you can then try to generate representations such that nodes that occur often in the random walk get embedded near each other. And this is the idea of two very popular models. One is called deep walk, and the other one is called node-to-vec. And that should give you an idea of how popular these ideas are. So here I'm listing the 8 most cited papers in this conference called CKDD conference. It's the most important conference in data science in the ACM. And you can see here that of the top 8 most cited papers, 2 of them are on representation learning graphs, so deep walk and node-to-vec. So this is a very popular problem, both in academia and also in industry, because it has a lot of application. But however, there are some very important questions that, especially if you're a practitioner and you want to deploy this in your application, you might be left in the open because these have not been addressed in the literature. So one of them is, especially in this context of link prediction, right? You're trying to predict whether there is a missing link between two vertices in the graph. And there are basically 2 ways you can do this. So like I said, you're giving these representations for 2 nodes. So these are the embeddings. And you can either apply dot products, which means like the pairs of nodes that have their representations with large dot products are those that you believe are links, right? So you assume that this dot product is related to the probability of a link. That's approach 1. But there's another approach that's also quite popular, and it's using a classifier. So in this case, you take representation of nodes and you concatenate them and give them to a classifier, usually like SVM or logistic regression. And then you assume that this classifier is going to tell you whether there's an edge or not. And it's not really clear like which with this approach is the best, and people apply them arbitrarily. So we wanted to give a systematic answer to this question. Another question relates to this hierarchical structure of graphs, right? And this, I think, connects a little bit with the talk that Eric just gave, that not only matrices, but graphs have this sort of hierarchical structure, right? That you have communities, and inside communities you have smaller communities, and you can keep zooming in. And this is very important, right? This has a lot of applications for uh, uh, many important uh, uh, like it has a lot of implications for many important questions that we have. For instance, how you can route information on the graph, right? So this hierarchical structure really matters. And however, when representation learning methods try to extract or make use of this hierarchical structure, they were often unsuccessful. So it has been shown that by changing the scale of random walks, which is a way to change the scale of the representations, there was really no impact on performance. So basically, these representations were insensitive to the scale of the process, which is it's an important limitation. So we want to understand why that's the case. And the way that you try to address these questions is by proposing a framework for understanding random walk-based graph embedding methods. This framework has three main dimensions. So one is what's the kind of random walk process that you care about? What's the similarity metric? Like which notion of similarity that translates connectivity in a graph to proximity in the Euclidean space? And the last is what's the algorithm that you use to optimize your embedding? So by looking at these three dimensions, we can categorize the main methods in the literature. For instance, deep walk uses a standard random walk process. The similarity metric is called pointwise mutual information, and the embedding algorithm is sampling. And you can also use this to categorize the existing work in the literature, and you can see there's plenty. But also you can find that there are some areas of this space that have not been explored yet. So this is also an opportunity to sort of like fill these gaps in this area, which is quite interesting. So again, we are trying to use this framework to answer the two questions that I mentioned early on. One is about how to do link prediction. The other one is how to exploit this hierarchical structure of graphs for multiple tests. And here I'm going to focus on the first question, just because of the time limitations. So, what we did is we took some of the data sets, the main benchmarks for the literature. So these are graphs with different numbers of nodes and edges and coming from different applications. And we looked at two main tasks. So one of them is node classification. So in this case, I give you a graph and nodes have labels, but you assume that you know the labels for only a few nodes and you want to predict the labels for the ones that are missing. So this is the first problem. And the second one is our link prediction problem that I have been discussing since the beginning of this talk, right? So I give you a graph, some of the links are missing, and I ask you whether there's a link between two nodes. And again, because of time, I'm going to limit our discussion to fixed process. So I'm going to focus on standard random walk process and also on embedding algorithm that's based on matrix factorization. But you can find more details about this on our paper. So let's look at node classification, right? And here I'm showing you what the expressions for the similarity metrics are. So on the left side, you can see the pointwise mode information, and on the right side, you see the autocovariance. So the similarity metrics, they are just functions of topological properties of the graph, right? So, and these are expressed in based on the stationary distribution of the process, right? So that's where the spies are coming from. So small pi is just a vector, that's the stationary distribution of the random walk process in the graph. And then big pi is just a different way to organize that in a matrix form. And then you have this M, which is the transition matrix of the graph. And you have tau is a way to control the time scale of the process. So if you increase tau, then you can account for larger scales. So you can see that the difference between autocovariance and PMI is just this log factor on this difference, right? And we're going to show that this actually has a lot of implications in terms of the performance of this method. So here I'm showing you the results for node classification. And so in the x-axis, I'm varying how much training data I have, and the y-axis, I'm showing you the performance in terms of macro F1. And you can see that the PMI outperforms autocovariance, which was kind of expected. This is what was assumed in the literature like for a long time, and that's why pointwise information is so popular. What was more interesting is what happened when we applied the same approach to link prediction. So here again, I'm applying the two similarity metrics, and I have both the So for each of these plots, I'm showing you on the x-axis how many edges I'm trying to predict, and then the y-axis, what's my precision. And you can see that here, outcovariance consistently outperforms pointwise information, sometimes by a lot. And this was something that was not known before because, again, this metric was not really uh, uh, that popular in representational learning literature. So it's a finding that was supported by the framework that we proposed in this book. And like to understand why this approach performs so differently, especially for link prediction, I think it's convenient to look at the embeddings that they generate. So here on the left side, I'm looking at pointwise multi-informational embeddings, and then on the right side, I'm looking at outcovariance embeddings. So this is, I'm just embedding 2 dimensions, right? So we can think there's an XY position that for each node that's determined by the embedding algorithm. And you can see that autocovariance, in a way, is very sensitive to the node degrees, right? So I'm marking here the hubs, or the nodes with highest degree, in red, and you can see that autocovariance sort of like puts these nodes in separate spaces, usually in the corner of the embedding, which you, in the paper, we are able to show that has a lot of implications when you use these embeddings for link prediction. So just to summarize, in this talk, I have described to you a framework for understanding random walk-based embedding. This is very important for many applications, especially like web applications where you're trying to solve problems such as node classification or link prediction. So these problems arise quite often. And we looked at 3 dimensions of this embedding approach. But actually, I focused on the similarity metric just because of the time limitations. But more details are described in a paper related to this project. And our contribution is that we unified random walk-based graph embedding methods, and we also were able to achieve state-of-the-art results for link prediction, and also understand the mood-scale structure of these embeddings. With that, I'll give you time if you have time for talks. Otherwise, feel free to reach out to me, and I'll be happy to discuss any details. Yeah, thank you so much.
Great. Thank you, Arlei, for the very interesting presentation. We actually have a couple minutes for questions here. So again, if everyone has any questions, please enter those in the chat box umbrella, and we'll read them here. We have one to get us started. So how does your approach generalize to other types of graphs beyond simple graphs?
Yeah, that's a very interesting question. So we actually have applied this method to other types of graphs, especially like a backup slide here. We apply this approach to polarized graphs, which are graphs where you have signs on edges and you have this community structure that's polarized. So you have agreement inside each community, and then you have disagreement across communities. And we are able to show that we can actually generalize this idea of autocovariance similarity to these sign graphs and achieve very interesting results. So here I'm showing what the performance is for baselines and also our approach. That's the last column. And you can see that in terms of precision, our approach really is able to outperform a lot of the baseline, especially for predicting negative links. So these are the red links that I'm showing you here in this figure. And so that was quite interesting because for a long time, it was believed that those links were really hard to predict, given that you don't have enough sufficient information to identify them. But we're able to show that using this autocovariance similarity notion, we are able to predict those quite accurately. Yeah, so thanks for the question. Any other question?
Great. Thank you, Arlei. So let's see. I actually don't see any question right now, but people might take a few minutes to digest some of this. So indeed, as Arlei said, please feel free to contact them, and this puts us exactly at 10:45. So everyone has been very, very cognizant of their own time. So thanks to all the speakers for this very interesting session today. Thank you all for attending. There's a brief break of 15 minutes now, and then sessions will restart at 11 a.m. Central Time. Thank you all for your time. Enjoy the rest of the day.